Hello, my name is Navid. I will be talking about our paper, Variant of VC Dimension with applications to depth-3 circuits, joint work with Peter Frankl and Slava Gryaznov. Let's recall VC dimension, which is a fundamental concept from learning theory originally, but also in combinatorics. Given a family of subsets of an n-element universe, we say that a subset is shattered by this family if the intersection of this set with the family produces all possible subsets. If you view this family as a subset of the Boolean cube, it means that on that particular set of coordinates, you can see all the Boolean cube, and we call this shattered. VC dimension, named after its inventors, Vapnik and Chervonenkis, is the size of the largest such set of coordinates for a family. And it's a measure of complexity of a set system, because if you have some coordinates which contains a large subcube, it sort of says that you have some level of freedom there. A very natural and basic question is to relate the VC dimension of a system to its size. So how large can a set be with a given VC dimension? And this was answered by several people. It's commonly now attributed to Sauer and Shelah, which gives the following bound, that if the VC dimension is at most D, then we can bound a family as a sum of binomial coefficients up to D. And this is tight. It's very easy to see that this is tight, because you can just take the Hamming ball of radius D, and it's easy to see that its VC dimension is exactly D. This is a very useful bound, and in applications that I'm interested in, it's usually enough, because if you have an exponential size family, then this bound already implies that the VC dimension is linear. So that's good, but sometimes we want more. It would have been nice if you could guarantee that the larger the family is, the closer we would actually get to n. But of course, it's not possible, because the Sauer-Shelah cannot guarantee anything over n over 2. So this is sort of the barrier of Sauer-Shelah and VC dimension. And we can see this by considering the Hamming ball of radius segment n over 2. So this has essentially, this is a constant fraction of the Boolean cube, but its VC dimension is only n over 2. So we cannot guarantee anything beyond n over 2. So our starting point, or the natural question, is whether we can somehow get around this. Of course, it's not possible, because this says that this is an impossibility statement. But can we do something about this? And the answer is yes, if we change the notion of VC dimension. So we're going to now consider a notion of dimension, which I find very natural, and it does allow us to beat this n over 2 barrier. We call this new dimension universal dimension for reasons that you will see. So once again, we have a family. Now we're not interested in a shattered subset of coordinates, but rather an R universal subset of coordinates. Okay, so we're interested in subset of coordinates where every subset of size at most R is shattered by F. And we call this size of such a subset the universal R dimension. And well, it just follows from definition that this is at least VC dimension when the parameters are relevant, we're in the correct parameter regime. So there's a hope that maybe we can prove better Sauer-Shelah type lemmas for this quantity. Okay, so What is the analog of Sauer-Shelah for this notion of dimension? So let's call this quantity U of n kr. So this is the largest, the cardinality of the largest cardinality of a system with from the n element universe of UR dimension at most k. And we answer this by going to hypergraphs and independent sets in hypergraphs. There are various ways of defining independent sets in hypergraphs, but we take the weakest one, which is, so and a set is independent if it does not contain any edge. So for instance, these black nodes, they do not contain any of these hyper edges of size 3, okay? An independence number is the, of course, largest, the size of the largest independent set. And what we're interested in is the maximum number of the total number of independent sets, the maximum total number of independent sets in a hypergraph, in an R-uniform hypergraph, where the independent set is bounded by K. So it's a Turan type problem, if you remember Turan type questions. So this basically asks, what is the smallest number of edges achieving this? But we're asking for the total number of independent sets. And we show that these questions are equivalent. And this follows from an old technique of Frankl. It's a squashing argument. So this allows us, this argument allows us to, we can basically assume that a family of maximal cardinality is downward closed. That if you know if a set is in a system, then all its subsets are also in the system. And then it's an exercise to see that this easily gives us a correspondence between these R universal coordinates and independent sets. And therefore these quantities are the same. And already this correspondence allows us to beat this bound. But what about this Sauer-Shelah type result? So now can we prove something precise? And the answer is yes, at least for the case of R equals 2, that is for normal graphs. We have Turan's theorem. Let's recall Turan's theorem. So this says that the unique graph with the smallest possible number of edges, with no independent set of size k plus 1, this is the disjoint union of k cliques of size n over k. So this is a unique extremal graph. And Zykov and other people, so this is a result which was proved many times in different languages and so on. So Zykov extends this and proves that actually this graph also uniquely maximizes the number of independent sets of any given size. And also in particular, maximizes the total number of independent sets. So therefore, we can just bound the number of independent sets in the Turan graph, and it gives us this bound, right? So because you can just pick at most one vertex from each of these cliques, and you have k of them. And this gives us an exact but Sauer-Shelah type lemma for universal 2-dimension. And this is better than what you can get from Sauer-Shelah and VC dimension. And it beats this barrier that I was referring to. So this is this says that we can arbitrarily approach n. So there is always a size threshold above which you know, you can have arbitrarily large U2 dimension. What about universal 3 and higher? So the situation is a little bit more difficult here, and but it's also not completely hopeless. So what we can show is that if for very high independence number, then the same result holds. So this disjoint union of edges is the unique, for the correct parameters, the disjoint union of edges is the unique hypergraph which maximizes the total number of independent sets. And the proof is not difficult. It's also non-trivial, and because this statement was known for the to-run problem for hypergraphs, that this is the unique hypergraph minimizing the number of edges with this independence number. But the proof is trivial there. But for bounding the total number of independent sets, we have to do more work. And it's based on an observation which allows us to, it's like it's sort of a, it's an iterative process where basically we pick an edge, we take any edge, and we can show that there is one vertex in this edge, the removal of which does not lose too many independent sets. So we do it one at a time until we arrive at an independent set. And of course, an independent set, of course, we know how many vertices it has, therefore we know exactly how many independent sets it has. And therefore, this gives us a total bound on the total number of independent sets. So this is, there is some issues here but the details are in the paper, but it's a non-trivial proof. And the general case, well, the general case seems to be that the same statement should hold. That is, this joint union of cliques of almost equal size should give the maximum number of independent sets. But note that this is different from the usual to-run problem for hypergraphs, because there it's open, it's widely open, and one reason is that there are many conjectured extremal instances. But here it really seems like if you want to maximize the number of independent sets, it's we also did some small computer search on very small instances. So it really seems like there's no reason not to take cliques. Okay, so now let's go to the application. So the complexity context in which we were thinking was the context of Valiant's program and depth-3 circuits. So we know that superlinear, we don't have superlinear second lower bounds, and even if you put a logarithmic depth restriction on them, we still know nothing. And Valiant came up with some program for attacking this problem. So let's consider this class of circuits. These are sigma 3k circuits. These are OR and OR circuits with bottom finding at most k. So I like to think of them as an OR of KCNFs. Valiant showed that with some nice graph theoretic argument that if we have a linear size log depth circuit can be written as a sub-exponential size depth-3 circuit where the bottom finding is, can be chosen to be n to the epsilon for any epsilon. So it means that if we have a truly exponential lower bound for depth-3 circuits, we get superlinear lower bounds for log depth. But depth-3 lower bounds that we do know are only of the form 2 to the square root n. So this is from switching lemma and so on. And what is interesting is that if we only consider constant bottom finding, then strong enough lower bounds would also imply superlinear lower bounds, but for series parallel circuits. And there are also some bounds known for constant Fanon, and so they are the form 2 to the Cn over k. This is C is a fixed constant, and the state of the art, this C can be chosen to be pi squared over 6, and this is from the PPSC paper, so the paper which gave the famous K-SAT algorithm, in fact, also gives a circuit lower bound. And if we fix the bottom finding to be 2, in fact, a maximally large lower bound is known. This is by Paturi, Sachs, and Zane. And that's all we know. But recently, Golovnev, Kolikov, and Williams showed that such a lower bound for bottom finding 16 would actually imply new lower bounds for general circuits. So this 16 appears from the proofs, so it's possible that one can prove such a result for smaller bottom finding. But what is the message here? The message is that this we should try to aim for results of the form this PSC results, but for a fixed constant, trying to prove maximal lower bounds. And this is somehow the motivation. So we were thinking about bottom finding 3, and yeah, this is what we were thinking about. What do we know in bounded depth circuits? Well, we have some tools. We have switching lemma, satisfiability coding lemma of PPZ, and then it's strengthening in PPSC, sparsification lemma, isolation lemma, Sauer-Shelah Lemma has been used several times, and so on. And this seems to be, well, maybe I'm missing something, but this is pretty much our toolkit. And you know, we have proved whatever we could prove so far with them. It seems that, at least to me, it seems that we should somehow accept the difficulty of circuit lower bounds and just try to expand this toolkit, in a sense that if we come up with some tool from which we can prove something non-trivial, I mean, not necessarily beating the state-of-the-art circuit lower bound, but something that something that you could not prove with the well-known techniques, then this should be considered a legitimate contribution and maybe a first step. And if we have enough of these tools, maybe finally we can prove strong lower bound. And this universal R dimension can be considered one such tool that we prove. We have some lower bounds that I do not know how else to prove. So let's start with bottom finding 2. This is, so I'm going to tell you the main idea of Paturi, Sachs, and Zane. Sure. Let's recall what a projection is. A projection is an affine space defined by equations of the following form. So it's, you know, it sets some variables to constant, and it identifies some other variables, or says that they are complement of each other. Paturi, Sachs, and Zane showed that a 2CNF formula with sufficiently many satisfying assignments in particular contains, in its set of satisfying assignments, a projection of large dimension. Now dimension, so this is an affine space, so you can think of a dimension of an affine space. And this is great because this allows us to derive from this lemma a lower bound for affine dispersers. And recall that affine dispersers are functions which are not constant under affine spaces of a given dimension. So in particular, if it's a disperser for sublinear dimension, we get maximally large lower bounds. Can we extend this result to 3 CNFs? By this result, I mean this precise statement about 2 CNFs. So the answer is no, because if we want to find projections, there are 3 CNFs, and we've written, it's in the paper, with exponentially many satisfying assignments, but with projection dimension bounded by a constant. So this statement does not hold for 3 CNFs. But we have general affine dispersers. So maybe it's possible to prove some other theorem which says that instead of a projection, we have we have a general affine space of dimension, large dimension. Can we prove such a thing? That I do not know. But still, we can do something with our universal dimensions. So the idea of Paturi-Saxon-Zane is that the projection dimension is exactly the VC dimension of the set of satisfying assignments. And this relationship is proved by our understanding of two CNFs, because two CNFs can easily be described by their implication diagraph. So we can easily analyze satisfying assignments. And but the same tool allows us to analyze this a little bit more closely. And actually, we can show that the VC dimension is exactly universal two dimension for two CNFs. So, and what does this mean? It means that for two CNFs, there is no difference between being shattered or being two universal. So this kind of syntactic definition of a two CNF forces some form of semantic constraints, and this allows us to improve Sauer-Shelah for two CNFs, and therefore a tighter bound for the size of depth-3 circuits bottom-finding 2. So this is tighter than, well, this is tight. Okay, I don't know if it's tight in terms of upper bound, but it's, yeah, it's a better lower bound than Paturi-Saxon-Zane. And one useful feature of this, again, to demonstrate that it's a non-trivial. So what is the non-trivial aspect of this? Because you can complain that, okay, we could already prove maximal lower bounds for affine dispersers of sublinear dimension. This is not adding anything. But well, this bound now allows us to prove non-trivial lower bounds for worse affine dispersers, if you care about them. But again, the point was to demonstrate some non-trivial application. In particular, if you consider inner product, which is an affine disperser for dimension n over 2 plus 1, so this result shows that if you have a 2 CNF which is consistent with inner product, consistent means that, you know, the satisfying assignments are contained in the ones of the function, then actually here we're looking at really the negation of inner product for simplicity. Then we have such a bound on the number of satisfying assignments, and I will explain why this is interesting later. What about 3 CNFs? So as I mentioned earlier, that was our main motivation to look at 3 CNFs. We can prove something here as well, although it's very, very humble. Consider 3 CNF. Consider a set of variables, which we can think of as coordinates, which are 3 universal for the set of satisfying assignments. Then the complement of this set is a hitting set for the CNF, meaning that every clause is hitting the complement. And why is that? The reason is that if you have a clause which is contained in T, the 3 universality implies that you can, in particular, falsify it and then extend everything else to a satisfying assignment, but that's a contradiction. So therefore, a large universal 3-dimension for the satisfying assignments gives us a small hitting set. And his hitting sets are useful for 3 CNFs because if we restrict on a hitting set, then the restriction is a 2 CNF, and we understand 2 CNFs. So in particular, we can combine. So if we have sufficiently many satisfying assignments, we can find a hitting set and restrict it, and then get a 2 CNFs, and then get a projection. So if we have sufficiently many satisfying assignments, then we get projections. And well, and we can find we can prove a precise bound on this. And it's also possible to prove this from switching lemma, but switching lemma implies that if you have sufficiently many satisfying assignments, then in particular, you can also find a large subcube. But so quantitatively, this is I can prove something better, and I don't know any other proof. And under the conjecture that I mentioned earlier about the unique hypergraph maximizing the number of independent sets with a given independence number, then this bound would even be better. So let me recall briefly what is the general strategy in proving this kind of lower bounds. The template is the following. So we have some function f which we want to prove that it's hard. Once again, we say that some formula is consistent with this function if the set of satisfying assignments are contained in the ones. And the main step is the following: show that every KCNF consistent with this function accepts at most t at some parameter t many satisfying assignments. Then we get lower bound for this depth-3 bottom-fanning case circuits, and for the simple reason that we can think of this such circuit as a covering of the ones of the function with satisfying assignments of KCNFs. So this is what PPZ does, what PPSC does, what this projection paper does, and so on. The problem is that this template fails in general for functions that are interesting. And again, we're back to inner product, and this particular question of studying inner product for bottom-fanning 3 was raised by Golovnev, Kulikov, and Williams. I mentioned one of the results earlier. But already even for bottom-fanning 2, the exact bound is not known, and it seems like it requires some new idea. So our result, our universal 2-dimension implies that every 2CNF consistent in a product accepts at most 3 to the n over 2, and this is tight. So if we want to apply this template, now we get lower bound of 2 to the 0.2n. But actually, we already know a better lower bound, and this follows from the lower bound for parity, which is in the PPZ paper. So what's going on? It seems like maybe we need to show some form of structural limit, some structural restriction on certain 2CNFs to understand these circuits. So what we show is that this 2CNF, which is consistent with inner product and has maximum number of satisfying assignments, is unique. So you should think of it as some kind of a Turan type. It's an analog of Turan theorem for 2CNFs. And the question is if we can extend this further. Is there a stability version of this? So stability means that maybe this object is not achieving the extremal quantity, but it's close to it. So does it still have some particular form? And does this particular form allow us to show that the circuit has to be large? We didn't put any results along this question in the paper. We didn't succeed, but we tried a bit, and it's not trivial. And it feels like maybe this should be something that we think about. So maybe we should a little bit become more. So this template is a little bit limiting. So we should really try to prove very specific type of result for specific functions, and then maybe we can get some lower bounds. Anyway, I hope you will read the paper and look at the details, and thank you for your attention.